Okay, well now let's see how we can test this expression in our experiment. All right, here, hang on one moment. All right, we just investigated Compton scattering, where a gamma ray is scattered off of a free charged particle. And with a little bit of work, we found this expression here. It's a nice expression for the energy of the scattered gamma ray. It actually looks a little bit nicer if we do one more step. Let's invert both sides. Then we have 1 over epsilon prime, energy of the scattered gamma ray, is equal to 1 over epsilon plus 1 over mc squared times 1 minus cosine of theta. A very useful result in itself. Okay? So same result, just more beautiful now. In fact, historically, people measured wavelengths instead of energies for gamma rays. And they used an expression like this. Since the energy for a photon is given by hc over lambda, then clearly the wavelength is related to the energy in this way. And we could rewrite our formula as the wavelength of the scattered photon is equal to the wavelength of the original photon plus hc over mc squared, or h over mc, times 1 minus cosine theta. So if you look up Compton scattering in the textbook, you might find an expression that looks like this. Okay, now, how do we test this with our equipment? Hang on one more moment. Here, let's take a look at how this works. So in general, our experiment will be set up like this. We have a radiation detector which is in the small form of a small volume, okay? And what we're going to do is to set our gamma ray source on top of that. There's our gamma ray source. But we're going to set it on top of a lead shield, like so. So the gamma rays from the source can't proceed directly to the detector. They have to scatter off of something else. And then at some distance, we'll set a block of aluminum, which contains lots and lots of free electrons. And this will be the object that the gamma rays can scatter off of. I think we'll make our gamma rays purple. Then what we expect is that gamma rays from the source can proceed to this block where they can get scattered and end up at the detector, okay? But gamma rays from the source can't go directly to the detector. And it may seem to you that this is a little bit complicated arrangement. There might be another simpler way of doing it, and there is. But in our case, we also want all of this to fit into a lead-lined box that currently houses our gamma ray spectrometer, okay? And that constrains us a little bit, but this should work fine. In addition, it turns out that Compton scattering is the most efficient when the scattering angle is close to 180 degrees, as this is. And by having an efficient process means that we don't have to use a very intense radioactive source. So we can use a test source that we can handle without any special safety equipment, which is definitely a good thing for everyone concerned. So that's how our experiment is set up. All right, Well, now I'd like to talk about how the detector works. The detector is shown here. It's a germanium crystal. Germanium is a semiconductor. And the semiconductor is normally insulated. But if we create free charges by exciting electrons from essentially bound states to free states, the electrons can move through the semiconductor very easily. The germanium crystal is sitting under a large applied voltage, 2.5 kilovolts, and it's at low temperature, 77 Kelvin. And under these conditions, even with the very large voltage, no current will flow because there are no free electrons to carry current. However, if a gamma ray comes by, well, I think I need my gamma ray to be a little bit more visible than that. If a gamma ray is absorbed in the detector, then the following will happen. The gamma ray's energy will go into exciting lots of electrons from bound states to free states. And the number of electrons excited will just depend on the energy of the gamma ray. A fixed fraction, about 30% of the energy, goes into exciting electrons. The rest turns into heat. Okay? So by measuring, if we could measure the number of electrons created, free electrons created, we would be able to measure the energy of the gamma ray. But in fact, that's exactly what we do. Under the strong electric field, the electrons are swept out of the detector, and they're measured as a pulse of current, which travels through a current meter on its way back to the battery. Okay? So that's how we detect the gamma rays. What I've called the current meter here is actually something called a multi-channel analyzer. It's a system that measures the height of the current pulse. And then based on the height of the pulse, it sorts that into one of, in our case, 2048 bins, and it adds one more count to the appropriate bin. Since the bin number is proportional to the height of the current pulse, and that's proportional to the energy of the gamma ray, what we're doing is sorting the gamma rays by energy, and then computing the number of gamma rays of each energy that have been detected. So this particular gamma ray has some energy, and so it would be one more count at that energy. Okay? And then as we collect more and more, we would develop a histogram showing numbers of counts at each energy. There might be one well-defined energy which is the energy of most of the gamma rays. Or it might look more complicated. But in this way, we get a gamma ray spectrum. And that's how it works. All right, I think we'll stop here. That gives you a general idea of how the experiment works. We're using a gamma ray spectrometer to measure the energy of the gamma rays. Oops. The gamma rays only reach the detector if they've undergone Compton scattering. So by measuring their energy, we're measuring E prime, the energy of the scattered gamma rays. Of course, we already know the initial energy. We measure that beforehand. And so using that, we can test our expression here. Does the formula for Compton scattering work? If we do this measurement for a range of different gamma ray energies, do we always get the proper value of E prime? Well, that's what we'd like to find out. Okay, let's stop here.